Hello everyone, welcome back to another Stat35 video. So in this video, we're gonna just cover just a few miscellaneous topics concerning functions. And this may be some stuff that you've sort of seen before, put together on your own, or things that you have seen sort of moved past, that it wasn't all that important at the present when you first saw it, but now we'll give some concepts, some names, and then also just touch on a few things that are just semantic type issues and things that are maybe running under the hood that are important to know. Okay, so the first covers composition, and I know that I've written some composition in class, and you've probably done it so far. So if I were to have some numbers, function composition works the same way in R as it works in math. I could do log x mean square root. Okay, so the idea being that in math, maybe I take f of x and then I have g of x, so that my argument x is passed into the function f, and then there's some output, and that output gets supplied as the argument into g, and then g evaluates on that input, which is the output of f of x, and then g returns the output based on this input. Okay, so I'll run x and we'll just run it and we get a number. So we have log of x, which is a vector. Then, well, yeah, they're all vectors, but vector of length 10, and then we apply mean of log of x, so sum of these numbers and divided by the total, and then we get that, and then we get square root. Okay, another sort of, I guess, lazier and more drawn out composition would be something like this. Out equals mean of out equals square root of out. So, and then we get exactly the same value as this. Okay, so I don't particularly like this, but sometimes internally inside of some function, and you don't really have a clear-cut way of coming up with descriptive variable names for each one of these intermediary steps, this is okay. I think you run the risk of typos along the way, or by declaring an extra quantity, you may, depending on how long this, well, actually, no. You may just open yourself up to errors. It's not the most elegant way to write it. That's not to say I don't do it, because I do occasionally. So deciding between these two, I always strive for this kind of thing, the composition in one line. However, it can become, if it gets a little bit, if there's too many functions in the composition, or the functions are rather tedious to write, not clear what they are, or require multiple arguments to be specified in them. So like maybe mean in a rm equals true, like this kind of thing. Now it's starting to get hard to write and see what's going on. Then I may break it up into smaller steps and do this. And if I don't have a clear-cut way of doing variable names in a descriptive manner, then this is what it'll be left as. So this is better, but can be tedious, cumbersome, hard to read, hard to write. Okay, then the last one, or a way that we haven't covered, and we will cover in a lot more detail as we move into the tidyverse portion of this course, and specifically using dplyr, is to use a pipe operator. So base R, if you've seen tidyverse before, base R has a pipe operator too, but the notation of these two quantities is going to be somewhat different, but nonetheless, we can do something like this. So I have x, I can take the log. Okay, I could then do mean, and then do, okay. So you can see that this is a pretty clean, coherent way of doing function composition that sort of has this nice sentence structure that accommodates these operations rather than just composition, which just sort of throws it all in, and then you have to do a tedious parenthesis check. The idea of this sentence structure being that I'm starting with an object X. I want to first log the elements of X, and then I want to take the mean, and then I want to square root it, and that's what I want to return. So this pipe is like an and then, and you can read this in a nice clean sentence. I have not used this, and the reason why is because I did not have the luxury of having a programming class like this one when I was learning R, and had I had it, I would have used this abundantly. And then by the time I learned tidyverse, or tidyverse was something that finally made my radar, then I started using the pipe operators within tidyverse. So without getting too far ahead of ourselves, this is a pipe operator. This is the notation for the pipe operator in base R. This is a pipe operator in dplyr, and we will use this a lot, just not right now. So composition, it's a strange story for me. I've mostly used these two, striving for use of this kind of string of function evaluations. However, I really like this right here, and I think that this is the way to do it, and it's certainly the way that dplyr does it, and dplyr has been I don't want to say revolutionary, but it's been revolutionary for data analysis in R. I think the tidyverse package is created by Hadley Wickham, and he won a Statistician of the Year award for recognition of this, much to the chagrin of the theoreticians and methodologists who research mathematical and applied statistics. But this is important, data wrangling, and making data wrangling easy and accessible and fast and readable and reproducible. So nonetheless, pipe operators, very important for data analysis, so we will continue on. Okay, scope of a function. Let me create a basic function with one argument that does some rather remedial task. Okay. All right, so what do I want to do here? Okay, so I have my function. You can see that it works fine. Sorry, I have my console over here. I've moved it over. I'm kind of trying this. Ever since I did the practice exam video, I'm kind of actually trying this out over here as my standard practice, but still looking around. Okay, so if I were to, okay, so first of all, actually, let me get a different variable name. Okay, so you can see the global environment down here. I have two things stored. I have this out and this X from the previous collection of exercises. Okay, so now here I have a function, f, and I'm evaluating it at y equals 2. So we know that y isn't accessed in the global, or like it's not a quantity in the global environment. The function creates its own environment internally, and then it's just discarded after the function has run. This is, and then outside of the function environment is the global environment itself, and this is the concept of scope. So here, if I were to supply an argument x, well, nothing happens here. X is just an argument that wasn't supplied, it wasn't used, and therefore nothing, no problem. Now, what happens if I do this? Okay, so x is missing with no default. Okay, so I've supplied an argument x and then give it a default. R complains. Now what if I do this? Okay, do you see what happened here? I have a function, an expression that I want to evaluate. However, this functional environment, there's no way x could be supplied in it because it wasn't an argument, right? So what the function did, it left its own environment and went searching in the global environment for a quantity x, which it found, which is this vector that I used in the previous exercise. So if we were to restart R, not supply x, this is going to complain. In fact, let's just demo it by getting rid of the global environment. Now what happens? So like, this is something that when you're programming, this happens all the time. This happens all the time it's happened all the time for me. As I'm trying to build some complicated function to do some complicated task. Before I had better programming practices, I would sometimes work inside the function environment and do stuff like this. And now it's going to complain. And I would be like, well, with R open, everything worked fine. And then it was a matter of figuring out what this error message is and what it meant, and where things, were. And then I'd have to go debug it. And, so this is something that when you're programming can happen all the time. So of course, in this case, it's easily rectified by providing another argument. And now it's going to complain because it says that the argument is missing. Okay. And here we are. Okay, so going back again, just to demo the point, if I don't have a function argument here, R complains because x is not found. It's something that is needed to, complete the task at hand. But if I had it in the global environment, then it works. So this is where you run into problems, but this is the concept of scope. A function has its own environment when a task cannot be completed with the quantities supplied in the arguments, then it's going to look inside of the next environment, the global environment, and in this case, the global environment, and then it's going to search for x. If it can't find x, then it's going to complain, and if it can find x, then it's going to run with that x in the global environment, creating a potential problem, but running successfully. Okay, so be careful on which arguments are supplied as you're building your functions. Okay. And of course here we get the error in which x is not supplied. Okay. Lazy evaluation. All right, so let's see here. So let's say I create my function and I do something very, very silly. Okay, so I have a function. If I call it, it's just going to, it's just going to run, right? Okay, so here, let's say I supply it with stop, do nothing. Okay, so first of all, oh, wait a minute. Sorry. I'm being silly. Maybe I need to do this. Okay. Right. Okay, sorry. My bad. I had to get a little bit organized there. Okay, so I create my function with an argument x, and I make my function essentially not do anything involving this argument x. Then even though I provide it with something that is supposed to just, throw an error message, right? Like that should get evaluated immediately. However, what R is doing, since the argument x is never called in anything internal inside the function body, it's just not going to actually evaluate the argument itself, and it's just going to complete all the tasks that don't involve that function and just proceed normally. So this is lazy evaluation. It's not going to do more work than it needs to when it's running its tasks. So x was never called inside the function body. Therefore, nothing happens. This isn't purely pedantic. It can allow you for it can allow for a function to do some sort of complicated time-consuming task only if the right arguments are triggered, and if they aren't, then it does a much simpler task. And this is something that actually can come up, but I don't have an example of it that can be communicated in sort of a short amount of time. Okay, dots. So this is, give me one, okay, wait. Come up with an example for this. Okay, so let's do h equals function x dots. Mean of x. Okay, so something silly. Let's do, so I have x, which is these numbers. Let's throw in an NA. Okay, and then if I do mean of x, that's going to complain because there's an NA. However, if I do NA.rm equals true, now it works. Okay, so then if I do h of x, right, it's going to complain. Or not complain, but it's going to throw NA. Now, if I do HNA.rm equals true, what happens? Okay, dots. So what happens here, and a lot of functions have this, we can, I mean, I just demoed that mean has it, but you can go to the help page and you can see it. That mean has two arguments, x dot dots. There's actually a few more in here. Oh yeah, usage, and then there's another page. So further arguments passed to or from other methods. So it's not the best description of what's going on, but this example actually demonstrates it perfectly. So in my function h that I want to do some task, so what I do is I allow the option for arguments to be specified that don't apply to h directly, but rather apply to some function inside of my function body, in this case mean. So here you can see that in this call, I didn't specify inside mean that the NA value should just be removed. I specified it in h, and R knew that by having the dots argument specified in each one of these, one in the creation of h, and then two specified here in mean, that na.rm equals true, which is meaningless for the function h, means something for mean and can work. So again, just looking at it, I have h, dots is an argument, dots is specified here at mean, and then I have this vector x, and if I, let me get rid of that, if I specify h, then I get an NA value because na.rm equals true is not supplied, and mean will return NA if there's an NA value present in the vector. So now if I do this, this thing is meaningless for h, right? There is no na.rm, nothing's happening here, but it's dots. And so that's going to get supplied to mean. Great. Now if I do, going back a bit, if I do y equals x minus 11. Okay, so that's my original thing. Now I'm back to this case. Dots wasn't necessary. I didn't supply anything for an h, nothing gets passed down to mean. In this case, the vector doesn't have NA, so everything just runs normally. Okay, very cool. That's something that is useful if you have, if you're building functions that involve function calls, and sometimes you may need to specify things inside those function calls. Then you can add a dots argument. Okay, functional forms. So broadly speaking, everything in R is an object, and everything you do in R is a function call. So all the tasks we're doing, or everything that we're doing to sort of manipulate objects, is in fact a function. The form that you're most familiar with is this prefix form, stuff like h of y, h of x. Oops. Yeah, nice with dots supplied. Or g. Yeah, these kind of things. So where you have the function name, parenthesis, arguments. This is prefix form. There's also infix form, something like 1 plus 2. So, we think of this as an operation of sorts, but it's actually a function. Everything in R is a function. And to see this, it's not that important, but I can write it in function form. However, this isn't going to work because this is not syntax that R recognizes as a function. So I have to do these little mini backslashes here. And now I get 3. Cool. So you can see it run in my console. Oops. Cool. Okay. Just out of curiosity, if I didn't do that. Yeah, it complains because this is not a function. Let's see what happens if I do. Okay. Yeah, I would need to use function composition. Again, I don't want to do that. Okay. So that's infix form. Replacement. So I have my vector y, my numeric vector from the integers from 10 going backwards to 1. I could give this a name. Actually, you know what? Where's out? Do I still have out? I don't have out. Let's go create out again. Let's just get rid of this. Actually, I don't want to. I have a good thing going with creating this with the NA and this thing. Okay, so we're back to start here. So now, out is just this number, this composition, this log of x mean square root composition, this thing right at the start. Log mean square root. Okay, so it's just a simple double or vector of type double with one element, length 1. I can give it a name. Names out equals some name. Okay, so now what happens? Okay, so you can see I turned it into a named vector. So this function right here, or this concept of replacement, I didn't really alter the vector in some meaningful way, but I changed some information or some attributes about it. And to do so, I had to supply a function call, namely this names one. Okay, so this is replacing some characteristic of a vector that probably doesn't alter the vector in some material way for some sort of like mathematical or data analysis task. Okay, and then last, we have seen this before, special functions which say for. That's a reserved word. Oops, didn't want to actually specify a for loop. If, these kind of things. Subsetting with the bracket notation, a little bit of autocomplete. So in I think the advanced R reference, you can find how to write these in this prefix form to make it explicitly clear that this is in fact a function. But without going through the exercise, it is a function. It's just this one has some special reserved words that you can't actually use for other tasks. Okay, so great. Okay, so now, oh wait, signaling conditions. And you've seen some of this stuff. I'm sure that you've seen it. But you could also directly create a message to be displayed. It's in red text, so it's scary, but it's not scary. It's just a message. I think the most common examples of messages are if you were to, and we haven't done it yet, but if you were to open up the tidyverse, it presents you with a whole bunch of information. That would be like a typical message. Occasionally, if you have packages, software packages that you load in, or sorry, I should just say R packages that you load in, sometimes those separate packages will contain functions with the same name, and that can be very confusing, especially if you don't know what's happening. And then so R will provide a message in that type of setting. So it's not like something wrong happened. It's just something happened and R is alerting you. But you can see here that we can explicitly call messages. Warnings are a little bit more stern, but your code would still run. Some warning. Okay, so this is red text also gives you, it says it's a warning message. Okay, where have we seen them before? Stuff like this. What's going to happen here, right? We have the concept of coercion applied to these two vectors the same length when we're doing this plus operation. Here we want to get anything, right? This just works. Yep. But now when we have vectors in different lengths that we're adding together, it doesn't have and then they don't divide, one's not a multiple of the other one, something will happen, but it will tell us that there's a longer object length, it's not a multiple of shorter. So the code ran, but we got a warning message because this is probably something that a user did not intend to do, more than likely. I don't actually think that there's ever been a case where I've added vectors in this way of two different lengths and added them, and it provided me output that I wanted. So I've been very happy with this warning message every single time it has appeared. So R was right, at least in my experience with stuff like this, adding up vectors, and the vectors happen to be of different lengths and they're not multiples of each other. So thank you, R. And then last but not least, errors. So I already showed one when we talked about lazy evaluation. So in this case, let's just run it again. This is a function with an argument x. The argument doesn't actually appear in the function body. Actually, let's go to this again. If 10 greater than, less than 11 x, return x. Otherwise, return 10. Okay. Interesting. Okay, I just wanted to know for myself so that so here x is being used inside of a. Oh wait. Oh, I'm being dumb. No, I want this. Okay. Okay, I was gonna say that was gonna be very counterintuitive for me. Okay, so anyways, right. So we have a function that has an argument x, and I'm giving it this thing that is technically. You can see that when I did it wrong, it threw an error message. Error in function at its input, do nothing. So this is a way that we can create error message. Is via via stop. Okay. So right, but in this case, in lazy evaluation, x wasn't called ever because this condition wasn't satisfied, so 10 got returned, right? Right. Okay, great. So we can use the stop function for errors. Now, sometimes this is actually pretty useful, even for beginners to R. When you're creating functions, you may want to think of some cases where users could supply some input that isn't appropriate for the function that you're working with. I think a common example is the functions that we're creating up here, where they all are meant to work with either integers or double vectors and not, say, logical or characters. If we supply logical, let's try it. what happens with, say, this one, where I have 2 arguments and I supply it with true, false. The answer is going to be 1, right? It should be. Yeah. So what happens is that y and x both get coerced to something of type, I believe, double in this case, and then 1 for true, 0 for false, and we get y squared plus x squared, and that would just be 1. Yeah. Okay. So, but the function itself wasn't intended to work on logical elements, so you may want to throw an error message to alert the user that you're doing something silly, and that gets into actually no, I don't want to get into handling conditions yet. So actually, let's just do this. Let's just take our function f and let's bring it down. Okay. So one thing we could do is stop if not. We'll say, let's do a simpler function. Let's just do this one. Okay. Stop if not is dot numeric x, otherwise do x. Okay. Okay, so here we get something good. We get 9, and here we get, okay, so you can see here that previously this would work. If I get rid of this condition, it's gonna work, right? Yeah, but yeah, we don't want it to do that. I mean, it's definitely not gonna work if I do something like this. Yeah. Oh, well, here we actually, I believe, get an error message. Yeah, non-numeric argument to binary operator. Doesn't work. Which, if you're paying attention, this binary operator is a function, but it just isn't in prefix form. Okay, so here we can see that with this error message supply, or with this stop if not, we are actually controlling, we're actually thinking ahead about input that we don't want users to supply, and we have a, we've caught it, and then we're supplying an error message. Now, however, this isn't the most convenient thing to read. This error message is, it tells you what's doing. Error in function evaluated character is numeric is not true. Something is going on that requires numeric, this thing. And we've caught it. Or sorry, no, this condition isn't satisfied, so it's not true. But that's not the most descriptive thing. What we could do is, if is numeric x, we could do stop, and then we can think of a descriptive error message. Argument x has to be numeric. Okay, now what happens? You can see the output message. Now that is incredibly useful. If I switch to x equals 3, it just works. The argument was numeric, so it worked. If it's 3.4, it works. Okay, great. So handling, okay, so that's error messages. Okay, so one brief aside here. This may be something that you've encountered as you're creating your own functions and testing them, and it may be a point of fear as you're submitting to the autograder. But if we are asking tasks that involve numeric inputs, either doubles or integers or something like that, then we haven't, and we weren't, and we won't try to trip you up by throwing a character vector and then saying, oh, you didn't do this, write this function completely. You didn't catch this obvious error case and stuff like that. So we aren't going to do that unless we explicitly say so in some sort of lab or quiz exercise. But that should be abundantly clear when we want you to do some sort of error message or some create one. Okay. So handling conditions. this is not going to be as like pedantic as it may seem, but there are certain cases where, or certain situations where you're creating a function where you expect that in the wide range of cases that your function can be applied to, that some of those cases are going to naturally just throw an error message for whatever reason. But however, in that case, you still want the function to perform, to continue going and perform, the subsequent tasks. I'm trying to think of a concrete example. The only thing I can think of is some optimization routines where there is a quick solution to them, but the solution is not very robust, and you may need a more tedious optimization method. And in that case, you may want to try the quick one first, but then if it throws an error message because that thing was quick and not very robust, then you would want to try the more tedious optimization method, which is more robust to some the inputs being supplied, but would also take longer. So in that kind of case, if the quick and dirty approach is widely useful in like 98% of cases, and the tedious one and is really fast, then that would be perfect for this kind of setting where all right, try it, didn't work, and on to the next thing, or try it, worked, skip the next thing type thing. Okay, so but we need to be able to write functions to actually do that task. One is this try catch. Okay, so give me 1 second to reread documentation because it's been a little bit. Okay, being mindful of my head here. Mechanism for handling unusual conditions, including errors and warnings. So I could do try catch. Okay, well I have my function f. So if I give it x equals 2, so remember, this is just gonna work. Okay, but if I do x equals a, then you can see, okay, so notice two things. Wait, that would work. Okay, so presumably it actually caught this error message. Now let's see, I need to condition. Give me 1 second here. Okay, so right, so we have an error. Wait, details condition. Yeah, okay, sorry, it's jogged my memory. It's a little bit confusing because I didn't see. Okay, so I can supply a function error. Okay, and I can have it do, okay, what is going on? Error equals function condition. Okay. So then here, if I do that, it's going to say NA. So basically what happened is this thing returned an error. Remember, X is not applicable for characters. We explicitly wrote it that way. It has to be type numeric. And then when it's an error, this function takes over and then does some task. In this case, it catches the error and then just returns NA. If I give this x equals 3 again, there will be no error. This part isn't triggered, and we just get 9. Okay, good. Okay, so right, that's it. That's what we're gonna, so we have some just more more function concepts that, you may have been wondering about, and this may help fill in the gaps for you. There's lots of further reading on this type of stuff provided on the webpage for this week. If you stay to the end of the video, thank you and take care. All right, bye.